Hello again. This is Math 2134 coming to you from the College of DuPage. The title of this lecture is Integral Properties, Areas Between Curves, and Smoothing Applications. Please be an active learner as you watch this video. When we think about a definite integral, we remember it can be regarded as the area under the graph of f over the interval a, b. So this definite integral from a to b of f of x dx is again the area under the graph of f over the interval a, b. So if we pick a c that's between a, b, we can see that the area from a to b is the same as the area from a to c, plus the area from C to B, and that's what this theorem states. So for C between A and B, the definite integral from A to B of f of x dx is equal to the definite integral from A to C f of x dx plus the definite integral from C to B f of x dx. This allows us to integrate continuous, piecewise defined functions. So you see this function, f of x is equal to 9. If x is less than or equal to 3, you see it is flat here. And for x greater than or equal to 3, it is x squared. So it's going up kind of in this u fashion there. So what happens is the definition of the function changes at x equal 3. So if we wanted to find the area from minus 4 to 5 of f of x dx, we would integrate the definite integral from minus 4 to 5 f of x dx, but we could take it up from minus 4 to 3 f of x dx, plus then we would integrate it from 3 to 5. You see there is a different definition of the function, so we have to split it up that way. So here, what you're doing is integrating 9, and that's 9x to the 0, so that is going to be 9x to the 1, and we evaluate x at 3 minus, because of the fundamental theorem of calculus, evaluating it at minus 4. Similarly, here we add 1 to the exponent, x cubed, and divide by the new exponent. So this is x cubed over 3. We evaluate this at 5 and then subtract off the value at 3. Here's the arithmetic. Again, you have to be careful minding your SI, G, and S's, but we get an answer of 95 and 2/3. Here is another problem. We're to evaluate the definite integral from 0 to 3 of the absolute value of 1 minus x squared dx. Now, as you know, the absolute value is always positive. So if we just took the function 1 minus x squared, we would have something that looked like this. It is a downward opening parabola shifted up by 1. But if we're taking the absolute values, I don't have the negative values, I have the positive values, so it changes to look like this. So you see, that means that the definition of the function changes depending on where you are. If we take the absolute value of 1 minus x squared, it's going to be x squared minus 1 during these intervals, there and there. And between minus 1 and 1, it's going to be this function. So the definite integral over that 0 to 3 then, going from 0 to 3, and this is representing the area, we have one function representing the function here, and it's a different function representing it here. So the area from 0 to 3 of that function is going to be the same as, we go up to where it changes, the integral from 0 to 1 of this function plus the integral from 1 to 3 of this function. We add 1 to the exponent and divide by the new exponents, getting this antiderivative, and we evaluate it at the endpoints using the fundamental theorem of calculus. Here, we do it term by term, getting this, evaluating it at the endpoints. So now we will stick in 1, subtract off sticking in 0, plus, this plus sign. We stick in 3 and 1. And we do the calculation, and I do expect you to be able to do these calculations. You will be tested on being able to do these calculations. You'll get 22 over 3 for this butterscotch colored area. In general, if we wanted to find this area here, A, that's between two curves, the blue curve and the red curve, we can find it by a two-step approach. We could find the area under the blue curve, which is on the top, getting this, and then we could subtract the area under the red curve here, and that would be this area here. If we generalize that idea, we have the following theorem that is an important application, and again, you will be tested on this. So suppose you have f and g are continuous functions. F is on top and g is on the bottom. It is important to remember who is on top. So the f is on the top, the g is on the bottom. So f is on top, then the area of the region between the two curves is found simply by integrating from a to b the definite integral of the function that's on top minus the function that's on the bottom dx. And you see we could summarize that up here because the integral of the difference is the difference of the integrals. And sometimes we will need to find where f and g intersect, as illustrated in the following example. So here we're trying to find the area of the region bounded by the graphs of f of x is a line 2x plus 1 and g of x is x squared plus 1. The upward opening parabola shifted up by 1. Now if you draw a careful graph, you see this is the picture, but we have to say where do these intersect. Now f is going to intersect with g when f of x is equal to g of x. So I set the definition of f of x equal to the definition of g of x. I rearrange things and I get a quadratic to solve, and I can solve this by factoring. And so this is going to be equal to, this is going to be equal to 0 when x is either 0, owing to this factor, or when x minus 2 is equal to 0 for x equal to 2. And from the picture, you know that, and you can substitute those values in, find out what the y's are. And from the picture, again, you do want to draw these pictures. You can tell who is on top, so the f is on top. So the area is computed by going the definite integral from 0 to 2 of the top function minus the whole of the bottom function. And this is a mistake many students make. So this is minus the whole of the bottom function. It can be simplified to this. The antiderivative of 2x is x squared. The antiderivative of x squared is x cubed over 3. We substitute 2, subtract the whole of what we get when 0 is substituted in, and we'll get 4 over 3. Please make sure you can follow these calculations. And certainly life is a word problem. There are big applications of this too, word problems. So a college student develops an engine that meets standards for emission control, and the emission is given by this function. E of t is 2t squared. And here is E of t is the emissions in billions of particulates per year at time t in years. Now suppose the emission rate of a conventional engine is given by this. Conventional C of t is equal to 9 plus t squared. So you see we have the E of t, which has lower emissions, and the conventional engines that has higher emissions. And so, at what point in time will the emission rates be the same? And so that's one question that people can ask. And part B, what reduction in emission results with the student's engine up to the time found there? So you see what we're going to do is we're going to find out where does the blue curve intersect with the red curve, and the reduction in emissions is this area here. Okay, so let's begin with that then. So we'll find when is E of t equal C of t. Well, we'll set the two equal. Use their definitions, and we'll do some algebra to get this to be t squared minus 9. That'll factor. So this goes from minus 3 to positive 3. But you see, what happens is we're only going from the year 0, so 0 is really going to be our bottom point, so we're going to be going from 0 to 3. And it's going to be t equal 3 is where the emissions will be the same. So the reduction in emissions is represented by the area of the shaded region right here. So that's the area between the curve on the top and the curve on the bottom. So this is the definite integral from 0 to 3 of the function on the top minus the function on the bottom. It's equal to this. The antiderivative of 9 is 9t. The antiderivative of t squared is t cubed over 3. We'll evaluate that at the top endpoint minus evaluating at the lower endpoint. Please make sure you follow these calculations, and we find 18. So over 3 years, the student's engine reduces emissions by 18 billion particulates. Now suppose that you have perhaps a temperature that varies over time, and so you can see the temperature is varying over time with this red curve. If you wanted to find the average temperature for the day, you might take 6 readings and say, I will read at 4 hours and at 8 hours and 12 hours, 16 and 20 hours. And the average could be found by taking the average of those readings, and there were 6 of the readings, divided by 6. Now, this computation of a moving average does have its limitations, though, because you miss dips that happen like going from here to here. It looks like there wasn't much of your change, but it actually dipped down. And so one way you can find a better measure of the average is to say, I'm not just going to do it every 4 hours, I'm going to do it much more frequently. And in fact, if you go to a limit as n goes to infinity of these sums, what you're going to find is that it starts looking very much like an integral. And in fact, the average value of t over the interval from 0 to 24 really ends up being, you do the calculation, 1 over 24. The definite integral from 0 to 24, f of t dt. That leads us to the following definition, and one that you should know of, because I could give you a function and ask you to find the average value. So for f, a continuous function over the closed interval ab, the average value y sub average is given by, you find the definite integral from a to b of f of x dx, and then you divide it by the length of the interval. So y average is equal to 1 over b minus a times the integral from a to b f of x dx. And geometrically, what that says is that this brown area, we're finding the average value that happens so that the area in this rectangle that you see is the same as the brown area. Let's do an example. So the question could be posed, find the average value of the function f of x equal x squared over the interval from 0 to 2. Well, it's going to be 1 over b minus a. This is the definite integral from 0 to 2 of x squared dx. Well, the 1/2 just sits out there in front, but the antiderivative of x squared is x cubed over 3. We evaluate it at the endpoints 2 and 0, and we do the calculation, and we get it as 4 over 3 is the average value of the function. That means that this rectangle, 4 over 3 in the y direction going from 0 to 2, has the same area as this butterscotch colored region. And there are other applications. This is talking about someone who's standing in line for a long time waiting. Now his speed in feet per minute varies over time. So his velocity as a function of time is given by this. from t being from 0 to 30, and that's minutes. And so what is from 5 minutes after getting in line to 25 minutes after doing so? What's his average speed? Well, you see it's always varying depending on how fast the clerks are working and the needs of the people who are in front of him in line. So it's this red curve that we find, but we wanted to know the average speed at which he is moving. It's changing all the time. So what we're going to do is it is 1 over 25 minus 5. That's the length of the interval. And we integrate from 5 to 25 this function, the velocity, dt. So the constants get pulled out, and the 1 over 20 is certainly out there, but the antiderivative of t cubed is going to be t to the 4th over 4. And the over 4 gets put in the denominator there. This is going to be t cubed over 3 times that. 3's will cancel. This is going to be t squared over 2. It's this one. And this is going to be 60t. We evaluated at the endpoints. Lots of calculations. Make sure you can do these calculations. So you formulate the problem, set up the integrals, then you calculate the integrals. I expect you to do all three. So we're substituting first 25, and we're subtracting off then substituting 5. And we're subtracting off the whole of substituting 5. We do all the calculations, and we find that this is the exact answer is 68.75 feet per minute. And to find out how far he moves, what you're going to be able to do then is multiply the length of the interval times the average. And so how far did he move? 1,375 feet. There's a final application in business called a moving average. Things can fluctuate very much, and it's hard to do analysis on that, but you might want to say what really is going on. For example, some data might have been uncovered that wasn't submitted, and it's going to make an artificial peak as well. So the idea is you have this very volatile red data, and you want to have a smooth curve, the blue data representing that. And so what we do is we define a moving average. F of average is going to be the length of the interval, and we go from x to x plus L. And here we find that that changes the red curve into the blue curve. And so you see you could get weekly averages, and this is taking everything going from in 3-week intervals. So you go from 2 to 5, 3 to 6, and so on and so forth. So get these values, and those are the blue curves connecting the dots. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.